Hi, year 11. We're going to look at something called inverse proportional inverse variation. Now, two variables are inversely proportional to each other if, when one variable increases, the other one decreases by the same factor. So, for example, if x is doubled and y is halved, that is inverse variation. If x is tripled and y is divided by 3, that is inverse variation. If x is multiplied by 4 and y is divided by 4, that is inverse variation. Now here's an example. The faster you go, the less time it takes to get to your destination. That's an example of inverse variation. So have a look. We've got a speed of 50 kilometers an hour, taking 120 minutes for the journey. And as our speed increases, what happens? The time taken decreases. As our speed increases now to 80, the time taken decreases. But more importantly, if you look at the original speed of 50, so have a look at 50 there, and the time taken is 120. And what happens when I double my speed to 100? The time taken is halved for the journey. So that's an example of inverse variation. Now, what is the equation for inverse variation? Well, the equation for inverse variation is y equals k over x. Okay, so have a look. That k there is called the constant, or the constant of proportionality, or it's called the constant of variation. Now, what about the graph of inverse proportion? Well, it's called a hyperbola. Okay, so the graph of inverse variation or inverse proportion is called a hyperbola, and this is the equation. We're going to look at what that looks like. So look at the first graph. You'll see here y equals 2 over x. It's got two pieces. The first piece is in the first quadrant, and the second piece is in the third quadrant. Okay, the other thing you'll notice is that the hyperbola gets closer to the x-axis, closer to the x-axis, and closer to the y-axis, and closer to the y-axis, but never touches those lines. Let's have a look at y equals negative 3 over x. Well, when the k value is negative, so when this constant here is negative, the hyperbola is in the second and the fourth quadrants. Okay, second and fourth. And again, you'll notice that the hyperbola gets closer to the y-axis, closer to the x-axis, closer to the x-axis, closer to the y-axis, but it never touches. So it never touches the x or y-axis. Now let's have a look at Desmos. We're going to have a look at hyperbolas just for a minute on a graphing application so you can see what happens as we change the value of k. So I'm just going to type in y equals k over x and then press enter. You can see that when k is positive, I'm in the first and the third quadrants. But when I make k negative, the hyperbola is in the second and the fourth quadrants. The other thing to note is that as the k value gets closer to 0, the hyperbola gets closer to the origin. And then as k moves further from 0, the hyperbola moves further from the origin. So have a look there again. Closer to 0 for k, closer to the origin. And as k moves further from 0, the hyperbola moves further from the origin. Okay, so what are some other key points? Well, you did the first part. That's done. What about the second dot point there? Well, the second dot point is the hyperbola has asymptotes at x equals 0 and y equals 0. Now, x equals 0 and y equals 0 are vertical and horizontal lines respectively. And asymptotes is a new word. It means it's a line that the function approaches but never touches. So let's have a look at x equals 0 and y equals 0. So x equals 0 is a vertical line that the hyperbola approaches but never touches. Okay, so that is x equals 0, and that is the vertical asymptote. Okay, and the line y equals 0 is a horizontal line that sits right on the x-axis. Okay, and that is the, let's change the thickness there. Okay, and y equals 0 is the horizontal asymptote. And there it is, that horizontal dashed line. Okay, now the asymptotes exist on the other function as well. So if you have a look, you can mark in the asymptotes on the other function. We do that with a dotted line. Okay, so those are vertical and horizontal lines that the hyperbola does not touch, but it gets closer to. Okay, so mark those asymptotes on your notes. Now, the other thing to note is that as x increases, y decreases, and vice versa. So you can see that. Now, as my x values are increasing, my y values are getting close to, my y values are decreasing as well. So as x is increasing, y value is decreasing. And we could actually write that down using this notation. So I could say that we'll just change the thickness here for a minute. So I've got a bit of room. There we go. All right, so here we go. So what we can say is x approaches infinity, y values get closer to 0, but a little bit more than 0, okay? So as x increases, y is approaching 0, y is decreasing. And you can see here, as x approaches, as x increases here, what's happening to, as x gets closer to 0, what's happening to the y values? The y values are approaching minus infinity, in other words, are decreasing. So over here, I could say as x approaches 0, y approaches minus infinity. Minus infinity is down here. So the thing to remember is as x increases, y decreases, and vice versa as well. As x decreases, y increases, doesn't it? So think about it. Up here, as my x values are decreasing, I'll just change to pan mode there. So you can see as my x values are decreasing, the y values are increasing. Okay, now the other thing to note is the hyperbola is called a discontinuous function because there are two separate parts. You can see that. Here's one part, here's another part. On the other function, here's one part, here's the other part. You can't draw these graphs without taking your pen off the page. So there's if you like, a discontinuity occurring. So two separate parts, therefore it's discontinuous. Now what about the domain? Domain is all real x except for 0. This is how we could write that. We go from minus infinity to 0, union with 0 to infinity. The range is all real y except for 0, and this is the other way we could write the range. Okay, so really, x equals 0 and y equals 0 are the only values which are not allowed for this function. And one way of thinking about that is why is x not allowed to be 0? Well, if you think back to some of the basic rules of mathematics, we can't divide by 0. So if I have y equals 2 on x, okay, now I can't divide by 0, so straight away just by inspection, x cannot be 0. And the other thing is I could rearrange this function. So y equals 2 over x, I could rearrange it to x, y equals 2, and I could rearrange that to x equals 2 over y. Okay, and straight away you can see that we can't have y being 0. So y can't be 0 because then I have division by 0 again. So that's another way of thinking about why x equals 0 and y equals 0 are not allowed. Okay, let's move on. Now, how about our table of values? We can think of a table of values for the hyperbola to understand why you never get to 0. So have a look. Try filling this in. So you're going to get, put x equals -3. You're going to get 2 over -3. Then you're going to get 2 over -2, which is -1. 2 over -1, which is -2. 2 over 0, which is undefined, so nothing goes there. 2 over 1, which is 2. 2 over 2, which is 1. And then 2/3. So you can see what's happening. The y values here are getting closer to 0, aren't they? But they're never going to get to 0. I can put 100 in here if I want to, or 1,000,000. If I put 100 in there, I'm just going to get 2 over 100, which is still not equal to 0. So you can see that the y values will just get closer and closer to 0, but never get there. Same over here. If I put in minus 100 over here, I'm going to get minus 2 over 100. Okay. So no, that's not correct, is it? Change that a little bit there. It should be 2 over minus 100. Same thing, but 2 over minus 100. There we go. But 2 over minus 100 is very close to 0, but not 0. So again, you can see that the y values will never reach 0, whichever way you go. You just can't get there. Okay, and let's move on to the next bit. All right. Now, for practical situations, we only use the first quadrant of the hyperbola. So you can see here, speed and time, they're positive quantities, which means we really only look at the first quadrant. So if you're looking at a practical situation involving the hyperbola, we just look at the first quadrant. Just some other terminology here. Another way of saying y is inversely proportional to x is we say y varies inversely to x. Let's have a look at drawing a sketch of the hyperbola. So we need a little bit of practice on that. So start off with now I'm just looking at the first quadrant here. So 2 divided by 0, that's undefined, can't do that. 2 divided by a half, we'll put that into a calculator, you're going to get 4, aren't you? 2 divided by 1, it's just 2. 2 divided by 2 is 1. 2 divided by 3 is just 2/3. So if I'm going to plot those points on the number plane, so let's do that. Let's just change colors for a minute. Actually, no, let's keep that as it is. So let's plot those points. We're going to have, well, undefined. In fact, we could put our asymptotes in here because we know x equals 0 and y equals 0 is where the graph can go. So I could put in my asymptotes. Here they are. So dotted line at y equals 0 because I know that's the no-go zone, and dotted line here on the y-axis. So they're my asymptotes. Now I'm going to plot 0.54. So 0.54 is just up here somewhere. Then 1, 2 is just here. Then 2, 1 is just here. And then 3, 2/3, well, that'll be a little bit more than a half, won't it? So maybe just about there. When you draw this, it's going to be a nice smooth curve, and you should show yourself, show the hyperbola getting closer to the axis but never touching. So let's try that now. So I'm just going to draw the hyperbola. And I'm showing that I'm getting closer, but I'm never touching. Okay, so there's your hyperbola. Now when you do these, just be careful. Don't do what we call the dead fish. The dead fish is when your hyperbola curls away from the axis. Okay, you don't want that. What you do want is you want to show that you're getting closer to the axis but never touching. Okay, that's what you want to do. Okay, now what about other hyperbolas? Now I should point out that I'm just doing this because this is in your textbook. This is not part of your syllabus, but we'll do it anyway. So this will just for your own curiosity, but it's not part of your course. You just have to know the y equals k over x. Now, let's just have a look at this hyperbola here. I'm going to rewrite it as y equals 3 on x minus 3. Now, we know that you can't have a zero denominator in mathematics. So x minus 3 cannot be 0. Okay, in other words, x cannot be 3. All right, so if x cannot be 3, that means I can draw a vertical line at x equals 3. Now, the other way of thinking about this equation is I could rearrange it. I could put this as x minus 3 is equal to 3. I could rearrange the equation. Yep. And then I can see here that I can't have a zero denominator again, can I? So y cannot be 0. So that means I've got vertical asymptotes at y equals 0 and x equals 3. So I can draw those in. So x equals 3. There we go. And y equals 0. So I know the hyperbola is going to approach those. There we go. And now I've just got to figure out where it goes. Well, if you remember, when we said that if this is positive, that was positive, we'd be in the first and the third quadrant. So this is similar. We're going to draw it in a similar way. So I'm going to be here. If you like, think of the dotted lines as your new quadrant guidelines, and here. Now, the only thing we need to know is the intercepts. So I'm just going to put in what happens at x equals 0. Okay, x equals 0, we get y equals 3 on minus 3, which is negative 1. So at x equals 0, y equals negative 1, just there. Okay. Now y can't be 0, so there is no x-intercept in this case. So we're just going to draw that in now. So show yourself getting closer to the axes. There we go. And over here, now if you're still not sure which quadrant you're going to be in, you can always do test points. You can always do a little table of values if you wanted to figure out which part of the number plane you're going to be in. So you could do, for example, if I put in 4, x equals 4, 4 minus 3 is 1, I get 3/4, which is 0.75. Okay, so 4, it'll be what, around about here, or something like that. So I can see I've missed, you can see my hyperbola should have been a little bit lower there. And over on the other side, you could have tried x equals, say, negative 2. What do you get? 3 over negative 5, which is negative 0.6. Okay, so at negative 2, that's right about here somewhere. So if I was going to fix that hyperbola up, just for a bit of accuracy, I'd just get rid of this bit there, and I would use my pen to just draw a bit of a more accurate hyperbola. So coming in a bit steeper there, like that. There we go. Okay, so you can always use little table of values to get an idea of where the graph should be. Okay, now let's look at and what's the domain and range, by the way? You can see the domain and range will be, for the domain, right, I would say all x not equal to 3, right? Or the other way of writing it is the x values go from, if you like, minus infinity up to but not including 3, union 3 to infinity. Now for the range, you've got all, the range will be all y not equal to 0, or we could say that the y values go from minus infinity up to not including 0, union 0 up to infinity. Okay. Now what about the last hyperbola here? All right, we'll do this the same way. First of all, we know that 2x minus 3, the denominator cannot be 0. Okay, so if I now solve that equation, I'm going to get 2x cannot be 3, and x cannot be 3 on 2, which is just 1.5. Yep. And over here, if I think of this as y equals 2 minus 1 on 2x minus 3. Okay, so I'm going to do this a little bit differently. I'll put the 2 on the other side to get this. And then I'm just going to swap this with this. So you get 2x minus 3 is equal to minus 1 on y minus 2. And you could make x the subject there, and if you made x the subject, you'd end up with x is equal to 3. Be a bit more complicated, actually. I've got no room to make the steps. But from there, you can see straight away that you can't have a 0 denominator. So you can say that y minus 2 is not equal to 0. So y is not equal to 2. Okay? So that means my asymptotes will be at x equals 1.5 and y equals 2, because those are the values which I'm not allowed to do. So I can put those in. So x equals 1.5. Put that down in the middle. Okay, and the other one is y equals 2. Okay, now, how do we know which quadrants the hyperbola goes in? Well, I want you to think of this equation in this form. I want you to think of it as y equals 2. I'm going to change the negative to a positive. I'm going to put the negative sign on top there. Now I'm going to have 2x minus 3. The reason being, we know that if you get a negative k value, a negative constant there, that you are in the second and the fourth quadrants. That means you're going to be over here and over here. Okay. Now, what about you could find the intercepts, of course. What would be the y-intercept? You put x equal to 0. What do you get for that? X equal to 0, you get 2 1/3. Yep. So 2 1/3. Now for the x-intercepts, it's a little bit harder. You've got to put y equal to 0 for that one. It's a bit of work to do for that one. X-intercepts, put y equal to 0, so you're going to get 0 is equal to 2 minus 1 on x minus 3. And then I'm just going to put the other is equal to 2. Now, do I have room for that? Yep. So now I'm just going to take the reciprocals of both sides. So x minus 3 over 1 is equal to 1 over 2. And that gives me x is equal to 3.5. Okay, so just about there. Okay, and the other intercept was x equals 0 y equals 2 1/3, so around about there. Okay, so sketch those in. So going through there, getting closer, not touching. And over here, going through the intercept there, not touching the axis, so showing that you're getting closer. Okay, so those two hyperbolas there, just drawn. We can write a little conclusion though. And that's this. If you've got a hyperbola of this form, a plus k over bx plus c, then you've got a horizontal asymptote at y equals a. So if you look over here, see the number there 2? Well, that corresponds to the horizontal asymptote at y equals 2. And over here, if you've got bx plus c on the bottom there, plus sign there after the a, then the vertical asymptote is at x equals minus c over b. Okay, and how do we get that? Well, we know that bx plus c cannot equal 0. Okay, so if you solve that for x, you're going to end up with x cannot be c over b. So that means your equation for the vertical asymptote is that. Okay, and as I said before, the other hyperbolas bit here, this is just a bit of extra notes, but it's not required in your syllabus. Only y equals k over x is. So that's it for graphs, and next video we'll look at how to find the equation of inverse variation.